Okay, we're going to start talking about determinants. And the introduction here, it poses a question. Given a square matrix, is there an easy way to know when it is invertible? And determinants are useful in answering that question, but that's not all there is to determinants. So let me give a little perspective. Now let's go back to what a vector is. A vector really is a one-dimensional object. You think of it as specifying a direction or a line. Any line through the origin is associated with a vector. Now, a vector also has a number associated, which is its length. Now, length tells you something about the vector, gives you an idea of the vector's size. Now, a matrix we can consider not as a one-dimensional object, but as a multi-dimensional object. Why is that? Because each column is a vector. So you have multiple vectors. Each vector can be thought of as a single dimension. So we have a multi-dimensional object that kind of brings together multiple vectors. And as the introduction says, the determinant is a number that's associated with that matrix. Now we're familiar with multi-dimensional objects in space. We are multi-dimensional objects. I am, at least I hope. I hope you are. I have 3 dimensions. Now, what's a number characteristic of a 3-dimensional object? If you think for a moment, the number that characterizes the size of a 3-dimensional object is its volume. Okay, the 3-dimensional object may have different shapes, but the volume is a single number that gives some idea of the size. And we're going to see that determinant is very, very closely related to volume. Right? So you can look at determinant that way. It has a geometrical significance. Another thing that's important about matrices that's not true about vectors is matrices can be multiplied. Right? And in some sense, multiplication is compatible with determinant. And we'll see how that works out in the rest of this discussion. Okay, so let's go back and take a look at the chapter. And we'll start with 2 by 2 matrices, which you may very well have seen before. Actually, you can talk about 1 by 1 matrices, which is just a single number. It's clear that when you take the inverse of a 1 by 1 matrix, you just take 1 over that number. And you multiply those 2 numbers on the right or on the left, it doesn't matter, you always get 1, which is the identity matrix in 1 dimension. All right, so it's clear that M is invertible if and only if this single component of the matrix M is 0. All right, let's go to 2 by 2 matrices. So we've seen several examples, and previous problems have shown that if this quantity M11, M22 minus M12, M21 is non-zero, then a matrix can be defined which is the inverse of the original matrix. Now you may recognize this quantity in the denominator as the determinant. If you remember how to do that in 2 dimensions, you do the diagonal entries multiplied together minus the off-diagonal entries multiplied together. And that's exactly what this formula expresses. So this expression makes sense if and only if this denominator is not 0. Okay, so I have an inverse for a 2-dimensional matrix if and only if this quantity called the 2-dimensional determinant is not 0. Right. Now you can extend that to 3 dimensions, and the formulas get more and more complicated. In 4 dimensions it's off the charts. You may have seen some kind of trellis method for computing determinants of 3 by 3 matrices. That's all very well and good, but those methods only work up to 3 dimensions. They don't work for 4 dimensions. So although it's nice for small examples, it really has limited usefulness. All right, so let's go back and try to understand where determinants come from. Now, there are different ways of motivating determinants. One of the common ways is through permutations. Now, permutation really is just a function. If you think of the numbers 1 through 5 here, we can take a function from the numbers 1 through 5 back to the numbers 1 through 5. All right, now a function means that I associate with each element in this set 1 through 5 another element in this set 1 through 5. And I can represent that this way. This actually is called a Tableau representation. But what this is representing is that the function takes 1 to 4, 2 to 2, 3 to 5, 4 to 1, and 5 to 3. You can actually think of this as a rearrangement of the elements in this 5-element set. If you had 5 markers marked 1, 2, 3, 4, 5, and you rearranged them in this way, you'd still have 5 markers, but in a different order. Right? So this is a way of representing this function, which is also a shuffle or rearrangement, and what we're going to refer to as a permutation. So permutation really is nothing but a rearrangement or a function. You can think of it in those ways. Right. Now, you see how I listed the numbers and then the function value, so I can write this way. This is the number and the function operating on that number. So we can write that systematically this way. And it's really not necessary to write the top row, because the top row is always going to be 1, 2, 3, 4, 5. So if I'll have the same information if I just write the bottom row, and we often denote permutations in that way. Sometimes square brackets, sometimes round brackets, but this is one way to denote a permutation. Now notice, if you've seen permutations before, there's another notation called cycle notation. This is not cycle notation. This is just Tableau representation in abbreviated form. If you don't know what cycle notation is, then just forget about what I said. All right. Now, there's some combinatorics or algebraic facts about permutations that we're not particularly going to go into. They're n factorial permutations. And if you've taken a probability class, you may have seen how to get that. There, you have n choices for in this case, for instance, one could go to 5 different values. And once I choose the value for 1, 2 can go to 4 different values, 3 goes to 3 different values, and so on. All right, so this is true. And every permutation can be built up by successively swapping pairs of objects. Okay? So, for example, to build up the permutation 3, 1, 2 from the trivial permutation 1, 2, 3, you can first swap 2 and 3, and then swap 1 and 3. All right, let's back up a little bit here. First of all, he says trivial permutation. Why is 1, 2, 3 the trivial permutation? Well, this is a permutation of 3 numbers. Okay. So this 1, 2, 3 that he's writing here, oops, where's my, okay, this 1, 2, 3 that he's writing here actually represents the second row of a tableau. So the permutation represented by 1, 2, 3 is actually in tableau form 1, 2, 3, 1, 2, 3. So it means 1 is taken to 1, 2 is taken to 2, 3 is taken to 3. So that's pretty trivial. You could also call that the identity permutation. Okay. So why does he say that this permutation 3, 1, 2 is built up by swapping 2 and 3 and then swapping 1 and 3? Well, if I swap 2 and 3 first, what would that give me? It would give me 1 go to 3. If I swap 2 and 3, that's 1, 3, 2. All right. So I'm doing that permutation first. And then, after that, he says I swap. What does he say I swap? After that, I swap 1 and 3. Okay, so the next, that would be, swap 1 and 3 would look like 1, 2, 3. Then this would be 3, 1, 2. So this is swap 2 and 3. This is swap 2 and 3, and this is swap 1 and 3. Whoops, sorry. Kind of got ahead of myself. 1 and 3. All right, now, if I do this first and then I do this, then what's going to happen? Well, let's follow it through. First, the first function takes 1 to 1. Let me use a different color. First function takes 1, so let me write it down here. I got one down here, so I'll do the composition of these two. The composition will take 1. If I start with 1, that's going to go to 1. So to find out where this one goes to, I got to go down here to this one, and 1 goes to 3. Okay, so if I do this function first and then this function, the final result is 3. So I have 1 goes to 3. All right, what about 2? If I start with 2, let's do a different color because it's pretty. Okay, we start with 2, that goes to 3. Now, after 2 goes to 3, where does it go to next? Well, I have to look over here in 3. All right, so from 3, where does it go to? It goes to 2. All right. So the 2 ends up going to 2. All right, now 3 had better end up going to 1, but let's verify it. 3 goes to 2. And then to find where 2 goes, I go here. 2 goes to 1, so 3 in fact goes to 1. All right, so the result is 3, 2, 1. So you see how I've gotten this other permutation from two swaps. Now this should kind of remind you of elementary matrix operations. We do row reduction by successively doing different row operations. Row swaps is one of those operations. We also have row multiplication and row multiply and add. But here we're showing that we can build up any permutation in terms of these primitive operations. In this case, these primitive operations are simply switching individual numbers in the set. Now here's where it starts to get interesting. For any given permutation sigma, there's some number of swaps it takes to build up the permutation. Okay? If this number happens to be even, then sigma is called an even permutation. If the number is odd, then sigma is an odd permutation. Right? Now, the interesting thing is there are several ways to build up a permutation with swaps. You can imagine how to do this in several different ways. I swapped first 2 and 3 and then 1 and 3, but I could have swapped 1 and 3 first and then done some other swaps and still gotten in the same place. But it turns out no matter how many times you swap, it will always take an even number of swaps to get from the original permutation to this new permutation. Now you can try it and see. It's always going to take an even number of swaps. There's also other permutations where it always takes an odd number of swaps. For instance, if I did just a single swap of 1 and 2, I could get that in several different ways. I could swap 2 and 3, then swap 2 and 3 back again, and then swap 1 and 2. But that's still an odd number of swaps. So whether or not the swaps are even or odd is a characteristic of the permutation. And that's why we can call permutations either even or odd. Very interesting fact. You may see how to prove this in your abstract algebra class. Okay. So we can define a function on permutations according to whether they're even or odd. And the way we do that is we say that if the permutation is odd, this sine function is -1, and if the permutation is even, the sine function is 1. So we just call this the sine of a permutation. This seems kind of arbitrary, but you might have thought that you could do 0 and 1, and 0 is odd and 1 is even. You could have done that, but it turns out that this function, sine of sigma, is a very useful function for defining the determinant of a matrix. Okay. And this is where it comes in, that the determinant of an n by n matrix is defined as, so this is going to be a little bit hairy, but we'll try to go through this. Determinant of m equals the sum over sigma. All right, so let me just go through this and then we'll go back over it item by item and see what it's talking about. Sum over sigma, sine of sigma, and then here we have m's. Now, the superscript refers to the row, and the subscript refers to the column. Now, here you actually have n different numbers. So this is a product of n entries of the matrix M. Okay. The superscript means that this first entry is from the first row, second entry from the second row, all the way down to nth entry from the nth row. This subscript means that the column is considered, the column index is considered as a permutation of the row index. So each column index here is a permutation value of the numbers 1 through m. Now what does that tell me? That means that these columns are just 1 through n in a rearranged order. Okay, so each m is going to come from a different row. Each m is going to come from a different column. But it's not always, the row and the column don't always agree. So there's some kind of rearrangement. Now, if you went back up here and saw the two-dimensional and the three-dimensional example, I went too far. Here we are. If we look at this two-dimensional determinant, this has the form that we're talking about. Look at the superscripts. And superscripts are the rows. I have 1 and then 2. Now, in this case, the subscripts happen to be the same. But the second term, the subscripts, or the columns, are switched. The subscripts here are a permutation of the superscripts. And notice the minus here. Turns out that this permutation that swaps 1 and 2 has a minus sign, because that's a single swap. Right? So you can see how this agrees with the formula that we just looked at. Now you can actually see the same thing here. If you look at all of these terms here in the determinant, you either have a plus sign or a minus sign. And then on the superscripts you have 1, 2, 3. The subscripts you have some permutation of 1, 2, 3. And if you check it out, the sign in front of the term agrees with the sign of the permutation that takes the superscripts to the subscripts. For example, this term here. Superscripts are 1, 2, 3. Subscripts are 1, 3, 2. How do you get the subscripts from the superscripts? Well, you swap 2 and 3. What kind of permutation is that? It's an odd permutation. That's why there's a minus sign. All right, turns out this one's even, this one's odd, this one's even, this one's odd. One interesting fact is that there are just as many even permutations as odd permutations. So there's always going to be the same number of plus terms as there are minus terms. Now I'm going to stop here, but we'll go on in the next video to talk about some properties of determinant. So I'm leaving you with this formula for determinant. Hopefully you can understand this cryptic formula a little bit better in terms of the description that I just made.